Hello, welcome to Electronics Education. This is Vincent Chang. In this lecture, I'm going to teach you how to investigate a magnitude response of a single time constant low pass function. From frequency response to Bode plot. Part 1. Magnitude response. From frequency response to Bode plot. Let's quickly review the circuit we have derived before. It's called single time constant circuit. Single time constant circuit. The step 1, for if we conduct the S-domain complex frequency domain analysis, the step 1, replace RLC with impedance. So R1, R and C are replaced by Z1 and Z2. Z1 equals R, Z2 equals 1 over SC. And then the next step is to derive the transfer function based on circuit theory. In this case, VO divided by VI, you can just simply apply the voltage divider rule. And then you can get this outcome. 1 over 1 plus S over omega. And the omega in the denominator, the root in the denominator is called pole. So this frequency, omega p, 1 over RC, is defined as the pole frequency. All right? So this is the passive, no gain. The passive RC. But in order to give you a general form of the single time constant RC, we change the numerator coefficient to a K. All right? So if the K could be 10, 100, if it's the operational amplifier, it could be 100,000. It could be very big. All right? So we give you a general form of a single pole, single time constant, low pass function. All right? So we change 1 from 1 to K. All right? So just give you a general form of a one single pole, low pass, single time constant, low pass function. All right? So next step is to replace. Remember the big picture of the S-domain analysis. The next step is to replace the complex frequency with J omega. Omega represents a physical frequency. The physical frequency. So look at the denominator. So S is now is replaced by J omega. So it becomes the complex. It becomes the complex transfer function. So same thing you learn from math. So when you look at a complex number and then you try to investigate, try to evaluate the magnitude of a complex number. So same thing in electronics here. All right, so next step is to investigate the magnitude response. What is the magnitude for this complex? The numerator is K, right? But what about denominator? The same thing. So real part and then imaginary part. So just take a square root, right? So real part, 1. 1 square is 1. And then the imaginary part, square. And then take a square root. All right? So this is the magnitude of the complex transfer function. All right? So we use the absolute sign to represent the magnitude of the transfer function. But this is the linear scale. But in many cases, almost all the cases in electronics, and then we use called the decibel, the dB, the decibel. The definition of the decibel in the log scale, not the linear scale. On the right hand side is the linear scale, but on the left hand side is the log scale. So it's 20 log base of 10. All right? 20 log at the base of 10. And then just take the linear the absolute value of the edge, the magnitude of the edge, the complex, so 20 log base 10. Base 10. And then this is the definition of the decibel. Magnitude in decibel. And log, because it's the division, right? So it becomes the subtraction on log scale. So 20 log K minus 20 log the square root part. So now, on the vertical axis, look at the spectrum, all right? On the vertical axis is the log scale. So 20 log, the magnitude of the transfer function. Hold on, all right? I want you to know all the detail about the magnitude response. Okay, I'm going to teach you all the detail about the magnitude response of the Bode plot. And then, because it's the log scale, it's not linear scale. See, in the linear scale, it's the 1. In the linear scale, it's the 1, 2, 3, 4, right? But in the log scale, it's the 10, 100, 1,000, and 10,000. All right, decade equal space for decade for 10 times. So 0.1 omega p, and 10 omega. So it's the log scale. Again, it's the log scale. And then what? Then low frequency. Let's just focus on our attention on the low frequency part on the left-hand side. So on the low frequency, how to define the low frequency? Let's say if the omega is much less than omega p. All right? So what do we mean by the much less than omega p? Let's say 10 times. All right? So omega for the 0.1 on the left-hand side, for when the frequency is much lower, low frequency part. And then what? Then this part, it's much smaller than 1, right? Omega, when omega is much less than omega p. And then log 1, this one, this symbol represents the negligible, all right? The square part, the square term is much less than 1, it's negligible. So log 1 is 0, so it means what? Constant. 20 log K is constant. What about the high frequency part? When omega is much higher than omega p, then what? Then 1 is negligible, right? Compared to the square term. And then the square root and the square can be canceled out. So now the equation can be simplified to 20 log K minus 20 log, simply omega over omega p. So in the log scale, this blue equation tells us what? In the log scale, log omega is a straight line. It's a straight line, all right? If I ask you, what's the slope of the straight line? What's the slope? How to specify the slope of a straight line? Of course, for the 20 log K, you don't need to specify because it's the horizontal, right? The slope is 0. But for this, for the non-zero slope, so how are we going to specify the slope? If your math is really good, you might be just pop out negative 20. But negative 20 of what? Negative 20 of what? On the left-hand side, the low frequency part is the low frequency asymptote. And this is the high frequency asymptote. So let's just put these two asymptotes in a junction, meet together at omega p. And this constitutes a diagram called Bode plot. This is what we call the Bode plot. It's the simplified diagram for a magnitude frequency response. All right? So now, let's come back to the question I was asking you. how to specify the slope. Let's start with the green point, all right? When omega equals omega p. And then when you increase the frequency, let's say 2 times, omega p to 2 omega p, the purple point, all right? So when you increase 2 times, then what? Then log 2 equals what? You can just punch the calculator, all right? So log 2 is 0.3. So 0.3 times 26, so 6 decibel, which means when you increase 2 times, then downgrade how many decibel? 6 decibel. So 20 log K minus 6 decibel. So negative 6 decibel per doubling of frequency. All right? So negative 6 decibel per octave per doubling of frequency. So doubling frequency, downgrade 6 decibel. And then what about the 10 per decade of frequency? If you increase the frequency by a decade, 10 times, then what? Then log 10 equals 1, right? Because the base is 10, and then 20 decibel. Are you with me? Can you follow me? All right? So omega equals 10 omega p, log 10 equals 1, and that means, which means when you increase 10 times, then downgrade 20 decibel. So this tells us what's the slope of the straight line. The second alternative representation for this slope is negative 20 decibel per decade, negative 6 decibel per octave, negative 20 decibel per decade. But what about at this frequency omega p? For actual curve, the blue line comes from 2 asymptote of the Bode plot. But in reality, the actual plot, there's a difference between the actual diagram and the Bode plot. Asymptotic Bode plot. There's a difference. But where's the difference reaches the maximum? At pole frequency, right? At high frequency, they almost coincide with each other. All right? At very low frequency is the concept of asymptote. But at this frequency, omega p is the biggest error. What's the error? What's the difference? We can calculate this. You can punch in the omega equals omega p. Then log square root of 2. So log 2 is 3. Is 0. Log square root of 2. So you can put the half, the concept of log. So 10 log 2. So 10 log 2 is 3 decibel. All right? 10 log 2, 3 decibel. So it's the 3 decibel frequency. For this reason, downgrade 3 decibel for actual curve. Omega p can also be called as the 3 decibel frequency. So many people, someone said the pole frequency, the other says this is the 3 decibel frequency. This is the reason. So here's the takeaway. In this lecture, I just want to focus, because a lot of detail, all right? But I want you to know all the detail. That's why I split the frequency response into several lectures, right? So in this lecture, we only focus on the magnitude response. So I think if I teach you the phase response, it will be too much, all right? So let's do one thing at a time. Just focus on magnitude response for this lecture, all right? So here's the result, the outcome. For the complex transfer function, what kind of complex transfer function? It's called single time constant, low pass. When signal comes in, and then different signal will experience different types of amplification or attenuation, all right? Now this is the outcome, the magnitude frequency response. Magnitude frequency response. So this is the takeaway. Next time when you look at this type of transfer function, so I want you to you can just write down the Bode plot based on the asymptotic diagram, asymptotic approach. You can also know the actual diagram in this way, right? And the biggest difference between the actual diagram and the Bode diagram is located at the pole frequency, which is also called the 3 decibel frequency. So we have come to the end of the lecture. Thanks for watching.